Okay, so we're back. In the previous video, I'd gotten to the point of talking about the two different ways of converting a load displacement curve to a stress versus strain curve. This first method is where you're presented with, from like a data acquisition system, load and extension data. And what you do is for each of those data points, you convert load, in this case it's in newtons, to stress by dividing the load by the cross-sectional area. And you convert extension to strain by taking the extension or delta L reading and dividing it by the original length. So the original gauge length here was 63.5 millimeters, and the original cross-sectional area is 61.1 millimeters squared. So if I took the load of 1400 newtons and divided it by 61.1 millimeters squared and converted that to newtons per meter squared, which is a Pascal, I would get 23 times 10 to the 6 Pascal, or 23 megapascal. And if I took this value of 0.03 millimeters extension and divided it by 63.5 millimeters, I would get a value of 0.0005. And so we do that for all of the data points in all of the numbers in both columns. And then we have a stress versus strain data set. So I just pulled in this, did my best to get a good graph that I could use. I know that my stress levels are going to go up to 234 megapascals. So I have this y-axis going from 0 to 250 megapascals. And then just had some trouble making the software give me an x-axis with values less than 1. So I've got points here at 50 and here at 100 and here at 150, and you would take those by 10 to the minus 4, so that point that value of 50 is actually 0.005 and the value of 100 is actually 0.01. And so the first data point has strain at 0.0005, which would be the first mark here, and a stress of 23 megapascals. So that's about there. So that's the first data point. And if I continue here, I've got all of the data points up until I have a strain of, let's see, 0.01, because the next data set is with a strain of 0.03, which be twice this distance to the right. So I couldn't fit it on this graph. And the goal here is just to get the linear part of the curve. Let's see, I'll use blue here. Just to get the linear part of the curve and some of the nonlinear part of the curve. That's all you need in order to calculate yield strength. All right. So we've got that. And so here's the data with a line drawn through to indicate my linear part of the curve and my nonlinear part. So I do that, and again, I'm doing that for a stress versus strain graph, not the load versus displacement graph. Okay, so one of the things that we want to calculate is the yield strength. And the yield strength is defined as the 0.2% offset strength. What does that mean? Well, in order to calculate this value of yield strength, once you have your stress versus strain graph, you go to your x-axis and you identify the point equal to 0.002 strain, and 0.002 is equivalent to 0.2%. So you find that place on your x-axis. And then you draw a line that's parallel to the original curve from that point, like this. Okay, so I've got now from the strain of 0.002 a line drawn that has the same slope as my original. And I can extend that line until it crosses the original data. There we are. So if I use this green line here for calculating slope, and I just need to choose 2 points in the linear region, or 2 points on this curve for calculating modulus. So I'm going to choose, let's choose this point and this point. So at this point here, I'm at a strain of, let's see, 2, 3, at x equals 0.003, and there's no units to that, and y is 40 megapascals. So that's my 2 data points. X is 0.003. Let's make that a little bit easier to see. X is 0.003 and y is 40 in megapascals. And then here, this data point looks like x is, I'm going to say 0.042. And y is 120 megapascals. Okay, so I have 2 points on the curve, and from that, I can calculate modulus. So modulus is the change in stress over the change in strain. So I've got 0.0042 minus 0.003. That's a change in strain. And then the numerator, we're going to have the change in stress, so that's 120 minus 40 megapascals. So that gives me 80 divided by 0.0012, and that will also be in megapascals. And let's see, gotta grab a calculator. $80 divided by 0.0012 is 66,667 megapascals. We'll say 60, really, as far as significant figures, we probably can't go beyond 2. So we would say this is 67,000 megapascals. Again, a megapascal is 10 to the 6 pascals. And that would be equal to 67 gigapascals, or 10 to the 9. And modulus is usually 1,000, on the order of 1,000 times greater than strength. So modulus is typically in gigapascals, whereas strength is typically in megapascals. Now, I want to just kind of try and help explain the name of the yield strength, that name of 0.002% yield strength. And so on this next slide, we talked a while ago, or at some point about the fact that here we are in the linear region, and any place in here, if I load within the linear region and then unload, I'll have zero permanent stress, a permanent deformation. But if I continue to load, in this case to here, and then unload, I have 0.002 strain. And so the yield strength is the stress at which I get, once I've unloaded, I get to 0.002 strain. That's why it has that name. Okay, so that's method one, where you're given basically load and extension data in some kind of a spreadsheet. And what the steps are involved are, first, converting the load to stress and the extension to strain, so that you've converted load extension to stress strain as far as two columns of data, and then you plot that data on a graph. And we only need to go so far with the data until we have some plastic deformation. That's method one. Okay, so method two would be if we were given the graph to start with, rather than given data. So here's an example. I've got load in newtons here on the x-axis or y-axis, and I've got extension in, let's see, it says extension is given in centimeters here on the x-axis. And so I could just keep the data points on the graph, not do anything with them, just leave them as they are. If I can change the y-axis to be stress instead of load and the x-axis to be strain instead of extension, then I could go with that straight away. All right? And we know that when the load is, for example, 2,000 newtons, we know that the stress is 2,000 divided by the cross-sectional area of 50 megapascals. As long as we have to make that sure we do the conversion, newtons per millimeter squared to newtons per meter squared. And we could take each of these extension dimensions, which are in centimeters, and divide that by the gauge length, which is given as 2 centimeters. So divide them by 2, get rid of all the units, and now I have strain. So if we look at the next slide, it looks like this. So now my y-axis is stress. That's great. To change my x-axis to strain, I would take each of these extensions, which are in centimeters, and divide them by the original gauge length, which is 2 centimeters. So just take each of these numbers and divide them by 2. So 0.005, let me get my little pointer, 0.005 extension is 0.0025 strain. Now my x and y axes are in stress and strain, so I can use this graph to calculate my modulus and my yield strength. All right, so again, for measuring yield strength, we take that from the graph, And the way to do that is we start with the equivalent strain of 0.002. So that's not, this point is 0.0025. So this point right here would be 0.002 strain. This point here where that's 0.005, that's 0.0025, but the one right before it, that would be 0.004, which would be 0.002 in the terms of strain. One, two, three, four, five. Okay. So it should begin right there. And then I need to draw a straight line, a line with the same slope as the original data. And note where that crosses my original data and looks like, let's see, I'll use a different color for that data. So right here, that's going to be where they cross. It should be a little bit more than 300, a little bit more than halfway between 280 and 320. So I'm going to call that 305 for yield strength. Now, of all of the things that we have to calculate from a tensile graph, the only one that absolutely requires us to use the graph is this one, the yield strength. And there have been attempts in the past, and I'm open to anybody who wants to try to calculate yield strength without having to use the graph. And in theory, it's possible. You would just calculate the slope, and then you'll have the equation for this line that begins at 0.005. So that you have the equation for that line. And then you'd have to use some curve fitting software to get an equation for the actual data line. But if you can do that, then the point and where both equations are equal to one another would actually be the yield strength. I have not had anybody be able to come up with a good predictive equation for the original data set. And because of that, it's necessary to plot this. Because calculating modulus, I just pick two data points, right? And find the yield, find the stress and the strain for the two data points and go from there. So that doesn't really require this graph, but yield strength does. All right, so we have this graph. I'm going to choose two data points. Make sure you do not ever choose the 0 point, because that's kind of a fictitious point. You have to choose two non-zero data points, and so I'm going to choose this one and this one. All right, so this point, the first point here, looks to me to be at x is equal to 0.001 strain, and y is 40. And here this looks to be at 0.01. And the stress level is pretty close to halfway between 160 and 200. We'll call it 180. Okay, so my modulus calculation is going to be 180 minus 40, change in stress, divided by 0.01 minus 0.001 strain. So that'd be 0.009. So I need 140 divided by 0.009. And that gives me 15,555. We'll call it, I guess we would, if we're only using two significant figures, we call it 16,000 megapascal or 16 gigapascal. All right. And I think I just threw that graph in case I needed one more, but I don't in this case. All right, so occasionally with some metals, we get a yield point. Instead of a curve that's linear and then just continues nonlinear, at the end of the linear region, there will be an extension that does not result in an increase in stress. So the load or stress will increase as I'm having extension, and then we'll get to a place where I have extension without an increase in load. And when that happens, it's that's you don't have to draw a line or a graph or anything. That is our yield strength. Some metals will give you a graph, give you an output like that. All right, so when I'm thinking about the response to the applied stress, I have a region that's linear elastic. It's in the green here. That's the elastic region, where this is linear. Following that, there is a region where the stress is increasing, pre-ultimate tensile strength plastic deformation, because the maximum stress is the ultimate tensile strength. So up until in this red pink area, that's the pre-UTS plastic deformation, and then there's a post-UTS plastic deformation. What's happening in those parts of the curve, what's happening at the atomic level, is something kind of like this. Right, this first slide is just illustrating elastic deformation. And the images here, this group of atoms, would represent that little square, white square in the sample as it's being pulled. So initially, they're all arranged like so. We apply a stress, and the bonds stretch, causing that segment, that portion of the overall sample to extend. And of course, we have Poisson's ratio. If we wanted to calculate the amount that this cross section decreases as this length increases. So the bonds are stretching, but that's it. And when the load is released, I go back to the original length, the original dimension. And so if I was looking at the actual force or load versus extension curve, I would see as the load is increased, I would see the extension increasing linearly. And if I unload, it goes right back to where it was with no permanent deformation. At the atomic level, when we have permanent deformation, this is what happens. So here's my initial, just like before. I apply stress and I get stretching of the bonds like I did before, but at some stress level, planes of atoms, how about this color? This plane of atoms slides past the next plane along this direction. So then maybe we could say it looks like that. So we've got this and that. So there's a specific plane and they're sliding past one another. That phenomenon, for lack of a better word, is called slip. And the slip is occurring on specific planes, depending on what metal it is, in specific directions. So individual bonds aren't breaking. What is happening here is there's some component of this applied stress that's a shear stress, and that component of the applied stress is enough to cause these planes of atoms to shift past one another. Then, when the load is removed, that shift stays there. The bonds stretching goes away, but the shift remains, and that's my permanent deformation. And so, as you can see in this image here, I've got my linear region, right, to there. And then it goes nonlinear, and wherever I stop the test, if I unload the sample, I see a permanent deformation delta L, which is what we've been measuring on their x-axis in the original data. All right, last slide is just an image of what happens, what the sample looks like during the test. So in the initial linear region, I've got a stretching of this gauge length, but that's it. It's just getting longer. And again, if I remove the stress, it will go back to its original length. At this is the point here where I start to get permanent deformation, but the image, the sample itself will get longer, but that's it. There won't be any change in the cross section at any point. So all I have here is it's continuing to lengthen, but now it's lengthening permanently. This maximum load level, okay, this is the stress. So maximum stress is equal to the ultimate tensile strength. And I'm not going to spend too much time referring to that, and I'll tell you why in a moment. Once I've gone past the ultimate tensile strength, the stress level will begin to drop. And that's because the cross-sectional area is getting smaller. So stress might be dropping, but area is dropping faster. I'm sorry, this is not stress. This is going to be load. The load level is dropping. I'll just say load. The load is dropping, but the area is decreasing faster. And so if that's decreasing faster than load, then the stress ultimately is increasing. So I see this load level drop, but the stress level is actually continuing to rise. And so the true stress is continuing to increase like that until failure. So I have elastic extension here, which is gone if I take the load off. I have plastic extension here, which is permanent, plus the elastic that I had here. Once I reach this ultimate tensile strength, this neck, it's called, forms, and the neck is getting smaller and smaller in diameter so that the load might drop on my output, but if I could divide by the instantaneous area, the stress would actually still be increasing. All right. In class, I'm just going to do some more examples of taking load deformation data and converting it into stress strain data.